My pleasure to introduce Phil Landry. So I got to know Phil when he was working at University of Chicago as a member of the LIGO collaboration, where his particular expertise is understanding the structure and composition of neutron stars from the data available from LIGO when the gravitational waves that are produced when these stars merge. And sometime after I left Chicago, Phil also left Chicago and now finds himself at Cal State Fullerton. But he's coming in today virtually to tell us about his continuing work on this topic. And I think we're all very excited to hear about what he has to say. Please take it away.
Okay, thanks a lot, Andrew, and thanks for the invitation to speak here. That's right, I'm going to be telling you about LIGO's neutron-star mergers and what they're teaching us about the properties of ultra-dense matter. So to start off, it's now been almost 6 years since the first binary black hole discovery by LIGO and Virgo. In that time, the collaboration has racked up 20 odd binary black hole merger observations and 2 binary neutron star mergers. So it's the neutron star mergers that I focus on in my work, and that's what I'm going to be talking about today. And you know, there's plenty of good astrophysics reasons to be interested in neutron stars. How do they form? What's the distribution, you know, of their masses and spins? But the question I'm most interested in is about their internal structure and composition. So what is the makeup and precise structure of neutron star matter? The reason that this is still an open question is basically that neutron stars are the densest material objects in the universe, and in their cores, they reach densities that, you know, exceed the density of an atomic nucleus. So that's too dense to reproduce in laboratory experiments here on Earth. And it's also too dense for first principles calculations like chiral effective field theory to get a handle on. And so we have a sort of coarse picture of the structure of neutron star, which is what I'm showing schematically here on the left. Basically, this is the density profile as a function of radius out in the neutron star. We know that the outer kilometer or two is the neutron star crust, where the densities are below about half an atomic nucleus density, half nuclear saturation density. There, the composition is neutron-rich nuclei with neutrons dripping out to form a neutron gas. You have this interesting phase called nuclear pasta, where the nuclei can get flattened or, you know, elongated into tube-like structures. This is physics that, in principle, we have a pretty good handle on, although it's, you know, very rich. There's a lot of interesting phenomena that go on there. As we move into the core region, approaching the nuclear saturation density, then conditions are getting close to idealized nuclear matter, which is basically like an infinite system of neutrons and protons interacting. Of course, here the system is asymmetric. There's more neutrons than protons. And up to 1 or 2 times nuclear density, we can calculate the structure from something like chiral effective field theory. However, as you get up further in density, then many body nuclear interactions become important. And you can even have the appearance of exotic species of particles. You can get pion or kaon condensates. You can get hyperons, so baryons that involve a strange quark, or even deconfined quark matter. And this complicates the picture and really makes it difficult to calculate the structure. So what do we do in this situation? Well, luckily, neutron stars represent the balance between relativistic gravity and the microscopic pressures that are coming from ultimately the nuclear interactions. And so this is why, you know, as an astrophysicist, we turn to observations of neutron stars' macroscopic properties to learn about the microscopic you know, interactions. I see there's already one hand up. So Mustafa, go ahead.
Sorry for interrupting so early on, but just this is a very nice summary of what's going on. So I thought I would take the opportunity to ask the question. So in the crust, you said it's neutron-rich nuclei. What is sort of the composition? Like, what are the main nuclei that are there? And also, presumably some of this is also leaking, I mean, the crust to the atmosphere part, right? So how does this transition take place, and what's in the nearby atmosphere as well?
Yeah, so those are good questions. I'm not sure that I am the expert on these topics, because I'm mostly interested in what's going on much deeper in the neutron stars. You know, in terms of the heavy nuclei, basically there's a point that's reached in the crust where you pass what's called the neutron drift level, and then the neutrons are going to leak out of the nuclei. So that's happening in the inner crust. In the outer crust, as far as I understand, you can get you know, heavy nuclei that are going to be very neutron rich, existing stably, and you know, exactly how that structure works, I don't really know.
That's fine. That's fine. So, yeah. Thanks.
No problem. So right, okay. So what I was saying here was basically the densities in the core, you know, are too dense for us to reproduce in the lab or to calculate with. So we want to look at observations of neutron stars to give us some picture of what's going on internally. Essentially, from nuclear theory, for the region of the neutron star above nuclear density, there are many different competing models that are based on approximate or phenomenological frameworks for treating the nuclear interactions. The thing is that they typically don't come with uncertainty estimates. And so you end up with this situation where at 2 or 3 times the nuclear density, you can get a factor of 10 or so uncertainty in the pressure in the neutron star. And you have this wide slate of models to pick between. That's each based on a particular treatment of the nuclear interactions. Mapping this to neutron star structure, so the neutron star mass and relation through the TOV equation of general relativity, which takes you from this equation of state, this pressure density relation, to mass and radius. We can go out and try and actually measure masses and radii to pick out which of these models preferred, and then that in turn will tell us something about the interactions that went into that model. So one sort of straightforward way of doing this would be, can we literally just go out and measure the radius and mass of neutron stars simultaneously? Yes, you can do that. The state of the art for doing that is something called X-ray pulse profile modeling, which the NICER Observatory recently did for a pulsar. That involves looking at some hotspots on the surface of a neutron star that are associated with the magnetic poles of the star, and essentially looking at propagation effects in the X-ray pulses that you see as the stars rotate. The X-rays travel through the curved space-time around the stars, and you can use that to infer the compactness, the mass to radius ratio for the star. But there are challenges to doing this accurately, namely the geometry of the magnetic fields on pulsars is complicated, and you have to sort of simultaneously fit for that geometry as well as the compactness of the neutron star. We can also get some information about neutron star matter from the terrestrial experiments, even though they don't really probe quite the right density, temperature, or proton fraction regimes necessarily. For instance, experiments with measuring the neutron skin or even heavy ion collisions can get constraints on the symmetry energy and its density dependence. The parameter for the symmetry energy, which is the difference between the energy per particle in pure neutron matter and symmetric and nuclear matter. The slope parameter is strongly correlated with the pressure around nuclear density. But again, if you want to turn that into information at higher densities, you need to make some modeling assumptions and essentially extrapolate. So gravitational waves end up being actually a perfect probe of dense matter and neutron stars, because the way that they're generated actually depends directly on the density profile and the distribution of mass within the neutron star. And so they come from the distribution of mass right down into the core, where we're most interested in figuring out what's going on. As I'll explain later in the talk, the way that the imprint of the neutron star matter is imprinted on the gravitational waves is very clean. It doesn't require too much sort of modeling. And the other thing is that when you observe gravitational waves from neutron star mergers, different parts of the signal actually probe neutron star matter under different conditions. So next, I wanted to show a video here of a neutron star merger and step you through the different stages and look at the waveform. I think I noticed a hand up though. Was there a question before I go on? Maybe the hand was taken down. So I'll carry on. So here's a video from the SXS collaboration of a simulation of the first neutron star merger LIGO and Virgo saw, GW 170817. At the bottom, you'll see the evolution of the waveform. The yellow are showing the emitted gravitational waves, and the inset here is showing the density profile, the mass, basically mass distribution. So the neutron stars are initially separated. This is the in-spiral stage. They come together, they touch, they merge. There's some matter that's ejected off, and then you have the merged remnant, which is oscillating, ringing down basically. In terms of the waveform, what happens during the in-spiral, the frequency increases up into a chirp in this chirping pattern. At merger, the amplitude of the waveform dies down. So I'll just go back, let's go through that again. So at merger, when the neutron stars come together, the amplitude of the waveform dies down, and then you have the post-merger part of the signal where the remnant is oscillating. And so basically there's these three parts of the waveform: the in-spiral, the merger, and the post-merger part. I'll be talking about the in-spiral and post-merger parts, primarily the in-spiral. I see a hand up. Paul.
Yeah, so I just have a quick question. What's the time scale of this merger? I have no sense of it.
Right, so for a neutron star merger like GW 170817, the in-spiral portion enters the LIGO band, at tens of hertz, below 100 hertz, and stays in band for a couple of minutes. But the final part of the merger, we're not actually able to resolve in this case because it basically leaves the band.
Okay, but this is something that's happening on the scale of minutes, not days or weeks.
Correct, minutes. And for the binary black hole mergers, then it's on the scale of seconds.
Okay, thank you.
No problem. All right, so let me move on here. There we go. Right, so taking a larger view of how neutron star matter fits into our understanding of matter generally in the universe, it's useful to think in terms of the Qcd phase diagram, which is what I'm showing here. So density, the x-axis, temperature on the y-axis. Neutron stars during in-spiral are cold, so their temperature is below the Fermi temperature. So you can treat them as being effectively zero temperature. And they, as I said, their core densities are, above the nuclear saturation density. So in this phase space, they live in the high density, low temperature region. This is a region of the Qcd phase space that's difficult to probe with other experiments. For instance, your heavy ion collisions are typically probing things at much higher temperatures and lower densities. At asymptotically high densities and at large temperatures, you can do calculations with perturbative QCD, which make predictions about matter. But in neutron stars, your densities are not really high enough, nor are your temperatures high enough for those to be directly relevant. So what's really cool about these neutron star mergers is they fill this kind of unexplored region of the phase space. And moreover, when the neutron stars merge, the remnant that results is no longer at zero temperature. So it's got a temperature of tens of MeV. And so you actually get up off the zero temperature axis and start probing the finite temperature regime. In addition, the ejected material becomes a site for heavy element nucleosynthesis and ends up, producing matter below nuclear density and kind of recycling things that way. So that's how these neutron star mergers kind of fit into the picture of the QCD phase diagram. And what I'll do next is do a really quick primer on gravitational waves so that we can get into the mechanics of how we actually, extract the dense matter information from these observations. Mustafa, question? Oh, I think you're muted.
Yeah, I've seen similar diagrams before, but I think this is a nice one, so I'll ask the question here as well. So can you just explain, maybe you said it already, the band with the orange dot at the end, what is that supposed to refer to?
Absolutely, yeah, I didn't say, but I should have said. So it is conjectured that there is a phase transition from nuclear matter to a deconfined quark state, even at zero temperature. So, this part of the phase diagram theoretically is not very well known, so there's a bunch of different ideas for it. But basically the idea is that even at zero temperature, if you go high enough in density, at some point you should hit deconfined quark matter. The phase transition here is indicated by this gray thing with, the orange being a triple point. So if you go up in temperature and density, then you should hit the quark gluon plasma, but we don't think that that's actually achieved in neutron star mergers.
Thank you.
Okay, no problem. All right, so quick primer on gravitational waves here. What are they? They're tensor perturbations in space-time governed by the Einstein equations, which when you linearize them about a flat background give you a wave equation. They propagate at the speed of light, and the most important feature, for us is that they're sourced by a time-varying quadrupole moment. And that's what makes compact binaries such strong gravitational wave sources. The mass distribution for a binary is, quadrupolar in nature. And by virtue of having compact objects, the most compact things in the universe being black holes and neutron stars, that's how you get the maximum amplitude, of your time variation in the quadrupole moment. So directly from the quadrupole formula, you can estimate the luminosity of a compact binary merger. It basically comes out to be the Planck luminosity, C to the 5 over G, which is 10 to the 59 ergs per second, corrected by a factor that depends on the binary separation. So these things are super energetic. The thing is that this immense power is only actually output for a split second right before things merge. Otherwise, it's suppressed strongly by the binary separation. As I mentioned during the video, the characteristic waveform for the in-spiral stage has this sweep up in frequency, the chirp. The gravitational wave frequency is evolving with the orbital separation. So it's, the loss of orbital energy through gravitational wave emission is driving the two compact objects together. That upsweep in frequency depends on what we call the chirp mass for the binary, which is just a combination of the component masses, M1 and M2. And so that's how we essentially measure the dominant combination of the masses, just from the frequency evolution. The other properties of the binary, namely the mass ratio, spins, and tidal effects, which I'll discuss more in a minute, impact the phasing. And the effect of a gravitational wave going through the Earth or going through our gravitational wave detector is to produce strain in the directions transverse to the propagation. So that's what this little cartoon is illustrating. And for a binary neutron star merger at 100 megaparsecs away, characteristic strains are on the order of 10 to the minus 21. If you multiply that by our 4-kilometer arm lengths for LIGO, you end up getting changes in the arm lengths due to this strain on the order of the diameter of a proton, which we can measure. I think that's pretty cool. So here's a picture of the LIGO detector in Hanford, Washington. How does it work? The basic principle is actually pretty simple. It's two rulers at right angles, two rigid rulers at right angles. When your gravitational wave comes through the detector, it's going to create these transverse strains that are going to alternate, alternately stretch and squeeze one arm and then the other. And all you're doing is measuring that pattern of stretching and squeezing, basically the amplitude and the phase. Of course, we don't do this with actual rigid rulers. We use lasers and mirrors so that we can carefully, and accurately measure the strain over time. Here's another little video showing exactly how that works. So if you imagine the gravitational wave coming down into the plane here, you get the stretching and squeezing of the arms. There's a laser that goes through a beam splitter. You're just doing a time of flight of the laser pulse to get the precise arm length measurement. And then the two pulses that travel the different arms are going to recombine and either constructively or destructively interfere, and you measure that with a photodiode. So it's an interferometer design, very simple in concept. All the technical challenge, all the magic happens in holding the mirrors at the ends of the arms perfectly in free fall, and in insulating this or accounting for all kinds of environmental noise, from seismic noise to trucks driving by on the highway, all sorts of things like that. So, there's a whole lot of work that goes into making this detector actually be sensitive. As an astrophysicist, I don't know the details of that, but I definitely appreciate all that stuff. So LIGO works as part of a global network. There are currently the 2 detectors in the US. There's the Virgo detector in Italy, and recently the Kagra detector in Japan came online. There's going to be a LIGO India built. I think it's currently under construction. Global network is great because it allows you to localize sources on the sky by triangulation, basically. Also, it's important to have more than one detector for the reason of identifying environmental noise and not confusing it for your astrophysical sources. Basically, you would expect the noise to be uncorrelated in all your detectors. So multiple observations are better. Here's what the sensitivity curve for LIGO looks like. It's this advanced LIGO gray curve. Basically, this is strain sensitivity on the y-axis, frequency on the x-axis, and anything above the gray bucket is observable. Overplotted here is a binary neutron-star merger for some sort of typical parameters. And this is like what I was saying during the video. We resolve for typical binary neutron-star mergers a lot of the in-spiral, starting at about 10 Hertz, and going into the late in-spiral where tidal effects become important. But we lose the signal. It goes out of band at about 1 kilohertz or so, just before it reaches merger. And the thing we can't currently see with our LIGO and Virgo detectors is the post-merger stage of the gravitational wave signal, where the 2 neutron stars have merged and the remnant is oscillating. And I'll talk more about that towards the end of the talk, but there's really rich physics there as well. And so we're excited for the next generation of gravitational wave detectors to come in the 2030s. Einstein telescope is the European proposal. There's a North American proposal called Cosmic Explorer that I'm also involved with. Those things will be great because they'll allow us to actually detect the post-merger signal. All right, so I had promised to explain how we actually extract dense matter information from the gravitational waves. It has to do with tides. So during the in-spiral stage, when the 2 neutron stars are close but still separated from one another long before they touch, tidal effects start to become important in the same way that they're important in the Earth-Moon system. The non-uniform gravitational field from the moon pulls a little bit more on the near side of the Earth versus the far side of the Earth, and that causes a deformation which is quadrupolar in shape. That's what's shown in the cartoon here. So during in-spiral, these 2 neutron stars are no longer perfectly spherical. They acquire these induced quadrupoles due to their mutual gravity. what we know from the quadrupole formula is that a time-varying quadrupole moment is going to source gravitational radiation. And so what this does is that the individual quadrupole moments induced by tides on the neutron stars end up adding to the orbital quadrupole moment and sourcing a little bit more gravitational radiation than you would otherwise have. And so the net effect of this is you radiate away your orbital energy a bit faster and you arrive at merger a little bit sooner than an equivalent system with point particles without any tidal deformations. So we observe this in the gravitational waves as a phase shift at merger relative to a merger of point particles. We can quantify this phase shift with this tidal deformability parameter lambda, which is an intrinsic property of the neutron star that depends on the equation of state the same way the neutron star radius does. You can calculate it given a pressure density relation for the star. There's an equation you can derive from the field equations basically that will supplement your TOV equation for the mass and radius. And it ends up being quite sensitive to the internal structure for reasons you can imagine. If your neutron star density profile is really centrally concentrated to make a really compact star, it's going to be much more difficult to deform than if you have a really big fluffy diffuse density profile. Then it's going to be very easy to bend out of shape. So the tidal deformability is really a proxy for what we call the stiffness of the equation of state, basically how large are those pressure gradients that act as the restoring force against gravity, and stiffer equations of state that produce physically larger, less compact neutron stars are going to give you a larger tidal deformability. So all else being equal, large tidal deformability means stiff equation of state, and then also for a given equation of state, a heavier neutron star will have smaller tidal deformability because it's more compact. So that's what's being plotted here, tidal deformability versus mass. There's a range of values that it can take on depending on the equation of state. And so just like we can measure masses and radii to pick out the true equation of state, we can try and do the same thing with gravitational waves where we're measuring these lambda parameters for each star instead. All right, so now we can actually get into talking about the gravitational wave discoveries, the binary neutron stars. I mentioned there were two that LIGO has reported so far. The first is, of course, the well-known GW170817 from a few years ago now. That involved two neutron stars of pretty typical masses, around 1.4 solar masses, merging to make a remnant of about 2.7 solar masses. This was a rather loud merger with a signal to noise ratio of 32 because it was nearby, which was great because that allowed us to localize it quite precisely on the sky, which enabled electromagnetic counterparts to be identified. So there was follow-up that found a kilonova, basically the afterglow from all the ejected material during merger. And then also there was a coincidence with a short gamma ray burst, which pinned down binary neutron star mergers as a source of gamma ray bursts in the universe. The other thing the loudness of this event allowed us to do was get a good measurement of the tidal effects. So in terms of this lambda parameter I was talking about, here's a contour plot of lambdas for the heavier and lighter components of the binary neutron star merger. This is a plot, basically the green shading is the posterior probability density. So the greener region is the more likely combinations of lambda 1 and lambda 2. And as I was saying, more compact stars will have smaller tidal deformabilities. So the fact that all the green is concentrated down in the bottom left-hand corner of this plot is telling you that GW170817 prefers very compact neutron stars, prefers what we call a soft equation of state, the opposite of stiff. And in particular, a few of these discrete proposals from nuclear theory for the high density equation of state are disfavored at reasonably high confidence by this observation. So here in the gray and black are predictions from individual nuclear theory models for the equation of state, and a few of them lie outside the 90% confidence contours for this measurement. This plot comes from follow-up analysis that was done in the year after the initial observation. So the first analysis of the gravitational wave data led to just an upper bound on the tidal deformability, lambda of less than 800. The follow-up analysis was a little bit more sophisticated in that there are correlations between lambda 1 and lambda 2, so the lambdas for the two stars, simply because the neutron star equation of state is assumed to be universal. We assume that all neutron stars have the same one. And so that just means that the lambda 1 and lambda 2s have to live along one particular curve in this lambda versus m space. And so when you take that into account, that bakes in some important correlations between lambda 1 and lambda 2. In particular, it grays out half the parameter space here because we always take mass 2 to be less than mass 1, and lambda is a monotonically decreasing function. And basically by using what is effectively prior information from your theory of gravity, we were able to better constrain the tidal deformabilities with this follow-up analysis and actually get the 90% confidence bounds on the individual ones down a little more constrained. I should mention also the kilonova observations place a lower bound on the tidal deformability that you don't get from the gravitational waves. So there is some support for zero tidal deformability, which would be the black hole value. So black holes have zero tidal deformability. We can't rule out, based on the gravitational waves alone, that one or even both of the members of the binary could have been black holes, but the fact that there was an electromagnetic counterpart tells us, of course, there was at least one neutron star in the merger, and very likely two. So, the multi-messenger aspect here can be important for constraining the lambdas. The thing is, this kilonova observation is just a less clean measurement of tidal deformability. Basically, it ends up entering through light curve models. If your neutron stars are more deformable, they're going to eject more matter, and you can do the mapping that way. So the second binary neutron star merger that LIGO has observed is called GW190425. It was a lot quieter, so its signal noise ratio was only 13, and it was also heavier. That was the most interesting feature about it. So one of the neutron stars was probably around 1.4 solar masses again, which is more or less what we expect by looking at the ones we know of in our galaxy. But the heavier component was closer to 2 solar masses. And that means that the total mass for the system is above 3 solar masses, and it's a clear outlier compared to the galactic population of binary neutron stars, which is what this plot is showing. So the galactic distribution of total masses is the black dashed line, and you can look at the blue posterior probability density for the total mass. In this event, it's clearly an outlier, and this is a hint that the gravitational wave population of binary neutron stars may not be exactly the same as the one we see with electromagnetic astronomy in our galaxy due to selection effects. So because the masses were larger, we expect intrinsically the tidal deformabilities to be smaller for this event. Also, this was a quieter detection. And so unfortunately, we weren't able to make a tidal measurement in this case. If you compare the tidal deformability we would have expected for these masses, based on what we've learned about the equation of state from 1708-17, you end up with this orange posterior, but what we measured was this blue posterior, blue shaded thing, which, in terms of statistical errors, is not really resolving the region that we expected the tides to be in anyways. So long story short, our only tidal measurement so far is from 1708-17. Yes, question?
So just, you mentioned this early in the talk, but I think I must have missed it a little bit, can you give a sort of just a twiddle understanding of what is the relationship, say in a simple polytropic model of the neutron star, right? Say P goes as rho to the gamma or something like that. How is that related to the equation of state? How is that related to lambda? Like what is in some model, it doesn't have to be universal.
So the dominant scaling of this lambda parameter is actually with the compactness to the inverse compactness to the fifth. So that's what this m to the -5 scaling is meant to indicate here. So you can think of this basically as scaling with radius to the fifth power over mass to the fifth power. There is a small sort of separate correction that is not captured in the radius's dependence on the equation of state. And that comes through this parameter that we call the tidal love number.
Okay. Right.
And that, that has its own dependence on the equation of state, but really the dominant thing is going to be this inverse compactness of fifth power.
Inverse compactness. Okay. Okay. Yeah. So, and it's 1 over m to the fifth or sixth is what you're.
Yeah. So it's r over m to the fifth power.
Right.
Yeah.
Okay. Thanks.
No problem.
While we pause, can you go back to that plot with the?
Oh yeah, you bet. This one here.
I mean, the one after this where you were showing the 1708, 17.
This one.
Yeah. So here, the idea is that the two stars will have different tidal deformabilities because the physics of the stars is different or the masses are different. Does it make sense to fit them independently of fitting the masses, for example?
So yeah, so this is a good question. The reason the tidal deformabilities are different is only because the masses are different. So in this analysis, we assume that the equation of state for all neutron stars in the universe is the same. We think that this is the case because they're all made of the same stuff as far as we know. I mean, when you get that dense, you're on some spectrum of density, central density or mass, and it's neutrons and protons up until you have maybe exotic particles appearing, but that's just a function of the density. So we believe there's one universal equation of state. And so the only thing that should change from binary to binary is the masses. And what you're asking about, what you're describing here is precisely the difference in the initial analysis of the data that just treated the lambdas as, independent parameters we know nothing about and tried to constrain them, versus this follow-up analysis the following year that used what we know about dense matter, and the way they're correlated to actually constrain things a bit better. Yeah.
Thank you.
Okay, any other questions at this stage? Okay, so I want to keep moving here because I notice we're getting through a good chunk of the hour already. Now that we've talked about gravitational waves and how tides imprint internal structure information onto the phasing, we can get into the weeds a little bit of how you turn that into not just measurements of tidal parameters, but actual information about the equation of state itself. So the simplest thing you can imagine doing is you have your nuclear theory models, you have your data, you can compare different models to the data and see which is favored. So this is Bayesian model selection. You compute a Bayesian evidence for your equation of state model just by integrating the gravitational wave likelihood against your prior distributions for the masses and tidal deformabilities that you expect to measure. And you can compare the Bayesian evidence that you compute for different models. So this is in LIGO analysis that appeared in 2020. Along the x-axis are arranged a bunch of different models from nuclear theory for the equation of state. And what's being plotted is the log of the evidence ratio. So this is a log Bayes factor of that equation of state versus the binary black hole hypothesis. So the hypothesis that actually tidal deformabilities were both 0 for this merger. And what you see as a trend is that the equations of state that are more compact, that produce more compact neutron stars, that are softer, are preferred versus the binary black hole scenario. So they're above 0. And the ones that are very, very stiff, meaning they produce physically large stars of a given mass, are actually disfavored. So what this is saying, again, is that GW 170817 likes small tidal deformabilities, compact stars, and it likes that so much, in fact, that it's more likely that one or both of the components were black holes than that one or both of the components, both of the components were described by a really stiff equation of state, like this MS1 thing, which was one of the ones that was like fairly strongly disfavored in this lambda plot earlier. So that's good in that we can use this to distinguish between different models, but we can actually go a step further. And instead of just taking things from the nuclear theory literature and testing them, we can actually try and infer the equation of state itself. This is also done in a Bayesian framework. The typical way of doing this is to parametrize the equation of state. So you adopt some simple phenomenological representation of your pressure density relation, for instance, a piecewise polytrope, where you say the equation of state is piecewise linear on a log-log pressure density plot. Your parameters are then just the slopes, these gammas, and some starting pressure. And you do a Bayesian inference algorithm whereby you calculate essentially the evidence, Bayesian evidence in favor of a particular combination of these parameters, and then you iterate over the parameters in a Monte Carlo algorithm. So in other words, pick some equation of state parameters, calculate the equation of state, see how well that compares to the data, and then assign that evidence times prior as the posterior probability of those parameters. Now iterate, and then in iterating, you're going to build up a posterior distribution over your equation of state parameters, from which you can just reconstruct the distribution over the equations of state given the parameterization. So in the analysis I showed before for GW 170817, this was done using this parametric equation of state inference method, using a spectral expansion in the adiabatic index, which is just like this slope parameter in the log-log pressure density space. And when you do that and look not at the tidal deformabilities, but actually at the equation of state itself, these are what the constraints look like. So green is showing the posterior 90 and 50% confidence intervals based on the 170817 observation. Relative to the prior, which is shown in pink, the main features are that at about twice nuclear density, so fairly intermediate densities in your neutron star, the equation of state is softer than predicted. So pressures are lower than we would have expected just based on our prior knowledge. And at high densities, the equation of state is about as stiff as we thought, and that's because we know there are 2 solar mass neutron stars out in the universe. And so the equation of state has to both match the soft, the small tidal deformabilities measured in 170817, but also have enough pressure gradients to support really heavy neutron stars of 2 solar masses. So what 170817 tells us basically is the equation of state has to do a bit of threading the needle between the softness at intermediate densities and stiffness at high densities. You can translate this into constraints on the radius. Again, the story is similar. At about 1.4 solar masses, which is where the neutron stars involved were, you end up with a radius constraint that has a median of about 11.5 or 12 kilometers, as opposed to before 170817, the median shown by the cyan contours here was maybe more like 13 or 14. So 170817 just tells you that the neutron star radius is probably a little bit on the small side of the range of predictions from nuclear theory. All right, so one other technical thing to do with inference I want to talk about is using a non-parametric representation for the equation of state instead of a parameterization. So the Bayesian inference framework is exactly the same. It's just that a parameterization, like I showed on the other page, on the other slide, sorry, is necessarily reducing complicated equation of state information down to a small number of parameters. That's a lossy transformation. Maybe you want to try and represent it in a more sophisticated way. And so with Reed Essek at the University of Chicago, when we were both there, we developed together this Gaussian process-based way of representing the equation of state for use in this inference algorithm. Essentially what you do is you try and emulate a wide range of candidate equations of state, which are the red curves on this plot, by building a Gaussian process model. That means you assume Gaussian covariance between the sound speeds at different pressures. So we build the model in sound speed versus pressure. You prescribe this Gaussian covariance between the sound speeds at every different density. There's a covariance kernel that depends on hyperparameters, and you optimize the hyperparameters and condition the model on a training set of candidate equations of state. And you end up through Gaussian process regression with an emulation of those equations of state, such that every realization of the process is a made-up equation of state that loosely resembles the things you trained it on. By working in this sound speed versus pressure space, that just ensures that the things that come out are causal and thermodynamically stable, as we would need for an equation of state. And we use some tricks to sort of make sure that even though we're emulating reasonable equation of state behavior, we are still covering the entire parameter space for viable equations of state. The long and the short of it is that this gives you an alternate way to generate equations of state to populate your prior distribution. And instead of sampling from a parametrization, you can sample from the Gaussian process equations of state in doing your Bayesian inference algorithm. If you do that and compare to what I showed on the previous slide, you also fold in the nicer X-ray measurements of neutron-star radius, which I mentioned at the very beginning of the talk, the existence of those heavy 2 solar mass pulsars. You can arrive at combined constraints on the equation of state from gravitational waves, but also from these other kinds of observations. Those are the contours shown in blue here. And this picture basically represents our sort of, present day state-of-the-art best understanding we have so far of the equation of state, whereby at about twice nuclear density, you have this softening in order to match the small tidal deformabilities seen in 17817. At high densities, you have to be reasonably stiff so that you can produce the 2 solar mass neutron stars. And the addition of the nicer measurement ends up bounding the pressure from below, because it measures the neutron star radius at a similar mass as 17817, but it prefers a slightly larger radius. So the error bars definitely overlap with what you would infer from 17817. The median is a bit higher, and that ends up sort of bounding the equation of state pressure from below. So in the end, the median estimate of neutron star radius after all these observations is about 12 kilometers, with uncertainties of a little bit more than 1 kilometer. All right, so in the last few minutes here, I want to touch on a few topics, few questions that we can try to address based on what we know so far about the equation of state. Firstly, what do gravitational waves tell us about exotic phases that might occur in neutron stars? First, you could ask about quark stars. So are there stars out there that are made entirely of quarks from crust to core? The answer is probably no, but I would hesitate to say that gravitational waves rule those out, completely. I think there's a lot of challenges for this picture. Namely, theoretically, you would have to have the deconfined quark matter state be more stable than nuclear matter, even at 0 pressure. There's challenges also in that it's tough to explain pulsar glitches with pure quark stars. There's a suggestion that they would be unstable to particular kinds of gravitational wave instabilities. And generally, pure quark stars have a pretty soft equation of state. So traditionally, it was difficult to make 2 solar mass neutron stars with these quark stars, but the theorists have found a way around that. Nonetheless, I think if there's going to be quark matter in neutron stars, it's more likely to come in the core, and you will either have a distinct hadronic phase and quark phase separated by a strong first order phase transition, or those 2 phases can coexist in a mixed phase with a smooth crossover between. There's evidence in favor of both these scenarios. Observationally, we can't rule either in or out. So, there have been a number of papers reporting, even proclaiming that quark matter exists in the cores of neutron stars. I think it's premature to claim, detection, but we certainly can't rule it out based on our current observations. And some sort of phase structure, some sort of phase transition could actually be helpful in reconciling the stiffness we need at high densities to explain the heavy pulsars and the softness we see at low densities with our gravitational waves. So kind of going further in this direction, maybe formulating the question in a more precise way, we can actually look at the sound speed as a function of density in the neutron star. And there's this long-standing conjecture, in particular this paper by Bedak and Steiner from 2015, that says that neutron star matter should have a sound speed that's always less than 1/√3, because that's the prediction for ultra-relativistic massive particles interacting perturbatively. This is the prediction you get for perturbative QCD at asymptotically high densities. And as long as there's nothing funny going on in nuclear matter, we should expect basically a clean interpolation down from nuclear matter where we can calculate things up to the PQCD asymptotics for the sound speed. If instead we find out that the sound speed exceeds this so-called conformal bound, then that would mean that there has to be some sort of strong interactions going on in the matter that makes it non-conformal. So one example of that is quarkionic matter, where you end up with effectively Cooper pairing of quarks at high enough densities. But basically the point is there's this conjecture that if we could show the sound speed in neutron stars exceeds 1/√3, it means there's an interesting phase of matter there. So these are the same constraints I showed on the previous plot, but now mapped into sound speed squared. The dashed line is this conjectured conformal sound speed bound. What you can see is that current observations definitely favor the fact that the sound speed would exceed this bound. They don't quite rule out the fact that it could be always below, but it's certainly more likely than not that this bound is actually violated in neutron stars. What does that mean for the matter? You know, in precise terms, we don't know, but I think odds are good that it's not just boring nuclear matter all the way up. I think it is probably the case that in neutron stars, there is going to be some you know, more exotic phase of matter at sufficiently high core densities. The final thing I want to say about this is, besides the question of just an exotic phase, you can look more specifically for evidence of a strong first order phase transition. So a sharp transition from a nuclear matter phase to a quark matter phase. In the equation of state, this shows up as a jump in the energy density at fixed pressure. And if it's large enough in your mass radius relation, it can actually lead to a disconnected hybrid star branch, whereby basically things with quark cores would live on this red branch here. Things with green, things on the green would be purely hadronic stars. And there's a regime in between where the stars are unstable. And so you can look for this kind of feature in your observations of neutron stars. In this analysis, same analysis I've been showing in the last few slides, you can sort the equations of state according to whether they have this hybrid star branch or not, and you can see what the data likes in terms of the constraints for those two classes. And basically the hybrid star equations of state are shown in green here, and they tend to be stiffer at low densities and to soften fairly dramatically in the middle, where they have this kind of flattening feature. So, you know, it's way too early to claim that this is evidence of a phase transition, but this is the kind of analysis that, as we get more data, could actually start to be picking out really distinct behavior, that could be a sign of these phase transitions.
Phil, just so I can understand, in the cartoon in the lower left there, would this also imply that you're saying there's some radius, some range of radii at which there just wouldn't be any neutron stars?
That's correct. And more than that, for this particular configuration, you can see there's actually what we call twin stars. So if you cut across in mass, there's masses for which there are actually two neutron star radii possible, one for the hybrid star, one for the hadronic star. And this would be a smoking gun for a first order phase transition. If we ever find two neutron stars with same mass but different radii or different tidal deformabilities, then we know there's got to be a first order phase transition. Yeah. So I think we're getting close to the top of the hour. I want to skip ahead a few slides. I'll just say that some of my recent work that's been super interesting has been collaborating with nuclear physicists to actually constrain the parameters of the symmetry energy and its density dependence from astrophysics and compare to experimental results on the neutron skin from the PREX experiment. I don't think I have time to go into that, but it is really neat to do these comparisons. There's all kinds of correlations in the literature between neutron star radii and these symmetry energy parameters. And what we're finding is that the ones that are published within a nuclear theory framework for this phenomenological treatment of the equation of state, they tend to bake in certain correlations based on the assumptions that go into the models, whereas just based on the astrophysics side of thing, without doing that modeling, we tend to get larger ranges for those correlations. But where I want to end up here is looking to the future and what's coming next in gravitational waves, because I think it's super exciting for dense matter science. In the 2030s, we will hopefully be building the third generation of ground-based gravitational wave detectors, Cosmic Explorer in the US and Einstein Telescope in Europe. And these will give us an order of magnitude increase in sensitivity. Cosmic Explorer is basically a LIGO that's 10 times bigger. So it's going to have 40-kilometer arms instead of 4-kilometer arms. And what that's going to do for you is, for neutron stars, your horizon for detection is going to be essentially out as far as there are neutron stars in the universe. Out to redshifts of 10 even. We'll be able to capture with Cosmic Explorer the complete binary neutron star population almost out to redshift 2. And what's particularly exciting for the kinds of tidal measurements I was just mentioning, with Cosmic Explorer, we'll get like hundreds of binary neutron star mergers with signal to noise ratios above 100 per year. So that means no more of the GW 190425s where we can't measure the tides. We'll be getting hundreds of things with precise tidal measurements, so we can really constrain the equation of state. Population scale observations are also going to be super useful. There's this idea, that I just mentioned of finding a smoking gun signal of a phase transition. As we sift through the whole population of neutron stars, we'll be able to find, interesting signals, outliers like that with more regularity. Post-merger gravitational waves. So our next generation detectors are going to have improved sensitivity in the high frequency range of 2 to 3 kilohertz, where we expect the post-merger signal. This is really great for dense matter science because post-merger remnant has finite temperature and has the very highest densities achieved in neutron stars. And so there's this really nice clean feature in the post-merger spectrum shown on the right here. There's a peak frequency that just has to do with the dominant oscillation mode of the remnant. Its frequency is tied intimately to the hot post-merger equation of state and the mass of the remnant. And so by measuring these things across the whole spectrum of merging neutron star masses, we can actually pin down the thermal corrections to the equation of state that are important for the post-merger remnant. And just to drive that home, here's the sensitivity curve that's projected for Einstein Telescope, one of these 3G detectors. And the difference between Advanced LIGO and Einstein Telescope is basically exactly what you need to resolve this post-merger signal reliably. So with that, since I'm pretty much out of time, I just want to go back to the QCD phase diagram. I've been through here, our present day neutron star mergers in orange, which are probing a few times nuclear density. We expect to see more with upgrades to LIGO. In the next few years, there's more observing runs planned. But the real exciting thing is going to be the 3G observations shown here in green that are getting the very heaviest neutron stars from the populations, the very loudest signals for tidal measurements, and then moving off the zero temperature axis in this QCD phase diagram to measure the post-merger part of the signal. So that's the picture for the future. I think it's really exciting. I hope you agree. And thanks for your attention. I'm happy to take questions.
Thanks very much, Phil. Clap on behalf of the group for the exciting and interesting talk. Looks like there's a whole lineup of questions. I think probably Matthew is first. Go ahead, Matthew.
Phil, thanks. That was a terrific talk. Very detailed, and I got a lot out of it. You early on when you're talking about the tidal deformability, I'm presuming that the two stars are phase locked, so that the only operative frequency is the orbital frequency as opposed to individual spin frequencies of the neutron stars. Is that correct?
So that's a great question. What I would say is it's probably not correct, but so far that's how we treat things in our data analysis.
Your parameters?
Yeah, and the question of actually the interaction between neutron star spin and tides is something that is not fully resolved theoretically. This is something I've done actually as a grad student. I did my grad studies much more on the theory side of things. And so it is expected that there will be spin corrections to the tidal response, but the dominant effect is still going to be the effect captured in this lambda parameter. So, you know, when you basically what happens is that when you add in neutron star spin, you can think of this tidal deformability I've shown you. That's the quadrupole response. L equals 2, n equals 0. When you add in spin, you get a Zeeman-like splitting so that the deformations now are m dependent. Yeah,
you get beat frequencies.
Yes, exactly. So then it gets very complicated, but the dominant thing is always going to be the L equals 2. One.
If looking ahead to these future installations, do you think it'll be able to probe the individual spins by looking at higher order Fourier components in the chirp phase or the pre-chirp phase?
Yeah, so we'll get a lot better spin resolution in future, mainly because, let's see, do I have a noise curve here? Yeah, so mainly because of the improved sensitivity for the bulk of the in-spiral. So, you know, from tens to several hundreds of hertz. Right now, for binary black hole mergers and neutron star mergers, we can constrain reasonably well the effective component of the spin. That's the component of the spin that's aligned with the orbital angular momentum, but we're really bad at getting the precessing component of the spin. Observing over more cycles with much louder SNR, we're going to be able to resolve that better. And, you know, then we learn more things about the interaction with tidal effects, but also more things about the population, you know, the distribution of spins, which is interesting for astrophysics reasons.
Okay, thank you.
No problem.
Yeah, looks like Mustafa's up next.
Already asked a lot of questions. I'll let Murid go first and I'll come back.
Sure.
Thanks. Well, thanks for the great talk. I really got much out of it. So coming back to this point about lambda parameter, I just wanted to have a rough idea, like how do you extract, like what do you set to be your prior to extract the lambda parameter? You know, like if you don't have any tidal deformation, then you expect the signal to be like that due to 2-point particles. So then is the idea that you scan at different frequencies, and so because of this deformation, you have sort of like stretching on the frequency axis and stretching on the amplitude axis. So you look at different bins and try to extract the lambda like that, because you have maybe more effect during the later stages of the in-spiral. Is that generally the idea?
So it's definitely true that the bulk of the tidal information is going to come from, you know, the late in-spiral, the last few cycles before merger. The way we actually extract the lambdas is part of the way we do parameter estimation in general, which is to have a waveform model. So you have your strain data that the detector is, you know, reading out, and what you do is you use the fact that we know general relativity to make a prediction for the waveform given the parameters. So, you know, you can calculate semi-analytically just a post-Newtonian expansion of the waveform that depends on the component masses, the component spins, and you can figure out how the tidal deformabilities come in. They come in at 5th order in the expansion. And, you know, the way you do the parameter estimation is essentially you sample from some prior distribution in the parameters, masses, spins, lambdas. The prior distribution is normally taken just to be, you know, uninformative. And then you compare the evidence for that particular waveform model with those parameters to the data, and, you know, then it's a Bayesian inference algorithm. So the answer is for the lambdas, we have models that have them. Those are what we would call our binary neutron star waveform models, and we're fitting for the values of them, you know, the values of the parameters. What we can do is compare the evidence for a binary black hole waveform model, which has no lambdas, and the evidence for, you know, a model that has them, to see which is preferred by the data. And, you know, there are some systematic differences between waveform models, not in the leading order treatment of things, but for instance, at higher orders in the post-Newtonian expansion, the details of the tidal phasing can depend a little bit on the waveform model, and this is you know, a constant issue in gravitational wave analysis dealing with the systematics of the waveforms. But luckily, we have lots of people doing numerical simulations and working on these waveform issues to just stay ahead of the game so that our systematic errors are always smaller than the statistical ones. Does that answer your question?
Yeah, thanks.
No problem.
Mustafa?
Yeah, maybe I can go ahead now. So here, for example, let's take this plot that's on the screen, right? So here, everything can be accommodated in some sense with some neutron-star model that you could get. Is there some, suppose we are looking for objects that were neither black holes nor neutron stars that could be fit. What would you be looking for? What would be the smoking gun signal that we can't accommodate within reasonably known physics?
Right. So one smoking gun signal would be some combination of the lambdas that does not lie on one of these dark gray curves. So violating this assumption that I mentioned, where we believe all the neutron stars have the same equation of state, tells us that lambda 1 and lambda 2 must be correlated to lie along some such curve. So if you ended up with a posterior distribution, you know, that was well constrained enough so that you could tell it really doesn't fit on one of these, you would know that one of the two was basically not a neutron star, or at least not a neutron star as we conventionally think of them. So right away, that's a smoking gun. If it turns out even, you know, not within one binary, but across many, many binaries, if you measure the tidal deformability at, say, 1.4 solar masses well to have some value, and one other star in the universe that you believe is a neutron star of the same mass has different tidal deformability, that's also a smoking gun, probably for this strong phase transition. So that's like, you know, probably one of the cleanest kinds of signals you could hope to see.
Great. Yeah, that's helpful. Thank you.
Yeah, actually, I have a similar question about the models on this plot. Am I supposed to imagine that there's a continuum of these nuclear structure models that just fill black lines throughout the whole plot?
Well, that depends on the nuclear theorist's ability to turn the models out. But in principle, yes, you could imagine cooking something up so that you're just blanketing the whole parameter space with these models. This is basically why we want to do more than just the Bayesian model selection that I was talking about, right? Bayesian model selection, you're comparing evidences for these discrete things, but what if it's not one of these, right? What if it's something different? You still want to be able to infer what's going on. And so that's why we turn to the phenomenological models, because we can generate them easily, so we can just carpet this whole parameter space.
And then another quick question, since we have a lot of people in the audience working on nuclear structure and heavy ion colliders, the models that are inconsistent with the measurements here, do they also make statements about what one would see at a heavy ion collider experiment? Or are they very separate because these are all zero temperature and that's very high temperature?
So I think it depends a little bit, but generally speaking, so at the base, there's some sort of you know, framework for doing the calculation. For instance, relativistic mean field theory, which gives you a way of treating the nuclear interactions, you know, in a way that's tractable. You can build out of that. You can go in different directions. So you can work, you know, in symmetric nuclear matter or pure neutron matter. You can work, you know, at zero temperature or not, and it all comes out of that, and you end up with predictions for, you know, the equation state in finite temperature regime, zero temperature regime, etc. As astrophysicists, we typically don't see any of that. We get the end product, which is the equation of state in the regime we're interested in. So what would actually be super exciting for the future would be if, as astrophysicists, we collaborate more closely with the nuclear physicists to get these models spanning across all the regimes that are of interest to us and simultaneously constraining things. In other words, instead of doing the phenomenological thing where we're cooking up probably bad models ourselves, just get the real ones from the nuclear theorists. The problem goes back to this challenge in, you know, what I described as calculating error bars for the predictions. Basically, you know, I think the nuclear theory calculations are so expensive that you can't just blanket the parameter space and get a posterior distribution over the equation of state yet. So that would definitely be nice, but maybe something for the future.
I see. All right. Any last questions for Phil? How about we call it there? I'll clap one more time and turn off the recording. Say thanks very much, Phil, for the excellent talk. I enjoyed it very much.